Welcome to today's explainer. We're taking something that usually feels like, well, kind of tedious, repetitive math, and we're turning it into a straight-up thrilling reverse engineering puzzle. We are going to crack the code of factoring quadratics. So forget about memorizing all those disconnected rules. Put on your detective hat because we're going to deconstruct these equations like absolute pros. Let's dive in.
So how exactly do you unscramble an algebra equation? I mean, building a math problem from scratch is one thing, right? But undoing it, man, that is where the real critical thinking comes into play. The central mystery we're tackling today is actually pretty simple. How do we take a complex, messy result and track down the original hidden pieces that created it? Section 1. The reverse engineering puzzle. Undoing FOIL multiplication. Okay, looking at this perfectly illustrates the difference. Over on the left, you've got your classic FOIL multiplication in action, right? You're multiplying the first, outer, inner, and last terms of x plus 2 and x plus 3 to build that shiny new quadratic, x squared plus 5x plus 6. That's a forward action. But take a look at the right side. That is factoring. It's the actual detective work required to reverse that exact same process and find our original ingredients. It's kind of like unbaking a cake. Section 2. The foolproof factoring method, cracking the x squared plus bx plus c code. All right, so here's your foolproof 3-step blueprint. Step 1, you set up your workspace by just writing out two binomials with an x, exactly like you see here. Boom, easy. Step 2 is where the actual puzzle solving kicks in. You've got to find two numbers that multiply to give you your c term, but, and here's the catch, those exact same numbers must also add up to give you your b term. And step 3, you simply drop those winning numbers right into your workspace. Done. Let's actually apply that blueprint to our very first target, x squared plus 5x plus 6. Now remember the rules of the game here. We need two numbers. They absolutely have to multiply to our c term, which is 6, but they also have to add up to our b term, which is 5. So any ideas on what those could be? To keep ourselves organized, we use a little table. Think of it as our detective's notepad to visually track all that trial and error stuff. In the first column, we just list the factors of 6. We've got 1 and 6, or 2 and 3. Simple enough. In the second column, we check the sums. So 1 plus 6 is 7. That doesn't match our middle term. But look right below it at the next row. 2 plus 3 equals 5. Bingo, we found our winning clues. Our factored answer is simply x plus 2 times x plus 3. Moving on to section 3, decoding the math signs, navigating negative numbers. So what happens when we throw some negative numbers into the mix? Take a look at this one, t squared minus 11t plus 28. Notice how we have a negative middle term, that minus 11t, but a positive last term, the positive 28? Think about it. If two numbers multiply to a positive product, but they somehow add up to a negative sum, what does that logic actually tell us about the numbers themselves? Let's consult our notepad again to prove it. To get a negative sum and a positive product, well, both of our clue numbers absolutely must be negative. There's no other way around it. So we test the negative factors of 28. Negative 1 and negative 28, sum is negative 29. Nope. Negative 2 and negative 14, sum is negative 16. Still no. But negative 4 and negative 7, perfect. They add up exactly to negative 11. Our final decoded factors are t minus 4 times t minus 7. Pretty satisfying, right? Now here is an even trickier curveball, a negative lost term. A negative c term, like the negative 5 you see here, means our two factors must have opposite signs. One's got to be positive, one's got to be negative. On the left, we've got a positive 4z middle term. That means the larger absolute value, the 5, has to be positive to, win the mathematical tug-of-war. On the right, our middle term is negative 4z, which means the larger number must be negative. Basically, the larger number always matches the middle term's sign. Section 4. Adding a second variable, the boss level. All right, welcome to our two-variable boss level, x squared plus 12xy plus 36y squared. I know, it looks super intimidating, but our structure completely holds up. That x squared up front just means our binomials still start with an x. The y squared at the back simply means the second terms of our binomials must both end with a y. The actual math to find the numbers in front of those y's, it's literally identical to what we've been doing the whole time. So let's track our factors once more. We need numbers that multiply to 36 and add to our middle term of 12. Scanning down the sums in our notepad, 37, 20, 15, 13, and bam! There it is right at the bottom. 6 and 6. They multiply to 36 and add to 12. We just attach those directly to our y variables, which gives us the incredibly satisfying answer of x plus 6y times x plus 6y. Boss defeated. And finally, Section 5, the prime number suspects, unsolvable puzzles. Okay, prepare yourselves for the ultimate mathematical curveball. I present to you this seemingly standard, totally harmless-looking trinomial, y squared minus 6y plus 15. We've set up our trap. We need two numbers that multiply to a positive 15 but add to a negative 6. Let's run the numbers and see what happens. Well, here is the twist. There is a total lack of a solution here. We know the factors must both be negative to get that negative middle term, right? So we list all the negative factors of 15. Negative 1 and negative 15 sum to negative 16. Negative 3 and negative 5 sum to negative 8. And, well, actually, that's it. We are totally out of options. Absolutely none of them add up to negative 6. No way. So, what's going on? Well, occasionally, the math puzzle is actually designed to be unsolvable. We call this a prime trinomial. Just like a prime number can only be divided by 1 and itself, a prime trinomial cannot be factored into binomials because literally no combination of whole numbers works. It's not you, it's the math. If you've checked your table completely and nothing fits, you haven't made a mistake at all. You've just uncovered a prime. So that leaves us with a pretty cool question. Where else in life might you benefit from working backward from a result to uncover its foundational elements? Honestly, factoring quadratics is really just a gym for your brain, teaching you how to reverse engineer complex problems. When you see a complicated situation out there in the real world, look for the clues, test the factors, and piece together the origin story. Thank you so much for joining me on this reverse engineering adventure. Keep questioning, keep deducing, and I'll catch you on the next explainer.